Okay, so let's talk about 12.1. You might hear my kids singing and carrying on in the background, but anyway, chapter 12. At this point in the course, we've talked about hypothesis tests on a single parameter. We did that in chapter 10. In chapter 11, we talked about hypothesis tests on two parameters. And now in chapter 12, we're going to talk about, in chapters 12 and 13, we're going to talk about hypothesis tests on multiple parameters. In chapter 12, we'll talk about the kinds of testing we can do on proportions, on 3 or more proportions. And then in chapter 13, we'll talk about the kinds of tests we can do on multiple means. Okay. But the first test that we're going to talk about in chapter 12 is called the goodness of fit test. And the way that the goodness of fit test works is that if we're trying to figure out if a particular probability model fits with the data that we're given, then we would use a goodness of fit test to determine that. So for example, suppose that we want to test whether bags of M&Ms contain 13% brown, 14% yellow, 13% red, and so forth. The null and alternative hypotheses here, if we're trying to test this claim, the null hypothesis would be that if I'm thinking of the brown candies as group 1 and the yellow candies as group 2 and the red candies as group 3 and so forth, then the null hypothesis would be that the proportion of candies that are brown is 13%. Proportion of candies that are yellow is 14%. And so forth, right? P3 would be 13%, P4 would be 20%, P5 would be 24%, and P6 would be 16%. Okay, that's the null hypothesis, right? That's the status quo. The alternative hypothesis is that at least one of these proportions is different than stated. So I'm going to just write that in words. So at least one of the proportions is different than stated in the null hypothesis. Okay, and the reason I'm writing it out in words is because if you write out all the possibilities, you're going to be here all day, right? Because it could be that it could be that the null hypothesis fails because P1 is wrong, but the rest of them are right. Or maybe P2 is wrong, but the rest of them are right. But maybe both P1 and P2 are wrong and the rest of them are right. Or maybe it's P1, P2, and P5 that are wrong and the other 3 are correct. Or maybe they're all right. So there's so many possibilities. You would just be here all day writing them all out. So it's easier to just write it in words and say at least one of the probabilities. And I'm going to use P sub I, right? At least one PI is different than stated in the null hypothesis. Now, you may recall that the proportion P of individuals with a certain characteristic is the same as the probability. It's the same as the probability that a randomly selected individual has the characteristic in question. So in the M&M's example, we can think of all the proportions as a probability distribution instead. Okay, so we're going to test the null hypothesis by determining how well the collected data fits with the distribution posed in the null hypothesis. And that's why we call it a goodness of fit test. We're going to see, is H null a good fit for the data that we collected? Okay. Here's some notation. Little n is the sample size as always. Pi is the proportion of individuals with characteristic I. EI is the number of individuals expected to have characteristic I. So it's the expected value for characteristic I. And we know that for a binomial variable, the expected value is n times p. So the expected value for characteristic I is n times pi. Okay. OI is the number of individuals observed to have characteristic I. You can't calculate OI. That has to be given to you. That comes from the data itself. Okay. And then K is the number of different proportions that we're testing. So in the M&M's example, K would be 6 because we're testing 6 different proportions. Okay. So K would be 6 in the M&M's example. Okay. Let's just practice computing some expected values. This one says, an urban economist wishes to determine whether the distribution of residents in the United States is the same today as it was in 2000. See the table below. If the economist randomly selects 1,500 households in the United States, compute the expected number of households in each region, assuming that the distribution of households has not changed since 2000. Okay. So this is not the data here. This is what the proportions were in the year 2000, right? So in the year 2000, 19% of people lived in the Northeast, 22.9% of people lived in the Midwest, and so forth. Okay. What we want to do is figure out if we take a sample today, 20 years later, right? So if we take a sample today of 1,500 people, how many of those 1,500 would we expect to live in the Northeast, the Midwest, the South, and the West if the proportions have not changed since the year 2000? So, I'm going to call the Northeast group Group 1, Midwest is Group 2, South is Group 3, and West is Group 4. Then the expected value for Group 1, people living in the Northeast, would be N times P1. That would be 1,500 times 19%, which I'm going to change to a decimal, right? 19%. I'll throw that into my calculator here in a second, but let's just write down the rest of them, right? E2 would be N times P2. So that's, again, 1,500, right? That's our sample size, but times the proportion of people who live in the Midwest, 0.229. E3, N times P3, 1,500 times 0.356. And E4, N times P4, 1,500 times 0.225. Okay, so let's see what those are. 1,500 times 0.19 is 285. 1,500 times 0.229 is 343.5. 1,500 times 0.356 is 534. And 1,500 times 0.225 is what did I do wrong? Oh, 1,500 times 0.225, sorry, is 337.5. Okay, so in other words, if we were to go out and collect a sample of 1,500 people, we would expect 285 of them to live in the Northeast, 343.5 of them to live in the Midwest, 534 of them to live in the South, and 337.5 of them to live in the West, right? So that's the idea there. My kids are going crazy. Okay, so with that in mind, right? Remember the OIs, those are our observations. They come from the data. The EIs, those are what we just computed, and that's how we compute them. K is the number of proportions that we're testing, okay? So, so the steps to run a goodness of fit are, as always, state the null and alternative hypotheses. Okay, and then calculate the test statistic. This is how we calculate the test statistic. You can see it's pretty nasty because we have to compute those expected values that we just did, and then we have to subtract them from the observed values, square it, divide by the expected value, and then add that up for each proportion that we're trying to test. But anyway, that's how you would compute it. And this test statistic follows a chi-square distribution. Once we get that test statistic, we can use it to compute the p-value, okay? And I didn't even write down how to compute the p-values, but the interpretation of the p-value is the same here as it always is, right? The p-value is the probability of obtaining the results that we obtained in our sample if the null hypothesis is true. So if the p-value is small, then it casts doubt on the null hypothesis, so we reject it. How small does it have to be? It has to be less than alpha, right? So that's the idea there. Of course, these two steps are going to be done in StatCrunch. To do those two steps in StatCrunch, we go to Stat, Goodness of Fit, and then chi-square test. right? Goodness of fit, because this is the goodness of fit test. We're trying to see if the null hypothesis fits with the data that we collected. So we're running a goodness of fit test. Chi-square test, because the test statistic follows a chi-square distribution. Okay, so stat, goodness of fit, chi-square. As always, there are conditions that you have to check in order to run this test. And as always, I'm not going to emphasize these very much. But just for your information, the expected values all need to be at least 1. And 80% of the expected values need to be at least 5. Okay? So no more than 20% of them are allowed to be less than 5, right? But so they all need to be bigger than 1, and at least 80% of them need to be bigger than or equal to 5. Okay? In order for you to run the test. That condition is pretty much always going to be met as long as your sample size is large. Okay, so if you've got a good enough sample size, those conditions are going to be met. Okay, let's practice. Let's practice running the test. So this one says, a sociologist wishes to determine whether the distribution for the number of years caregiving grandparents are responsible for their grandchildren is different today than it was in 2000. According to the United States Census Bureau, in 2000, 22.8% of grandparents have been responsible for their grandchildren less than 1 year. 23.9% of grandparents have been responsible for their grandchildren for 1 or 2 years. 17.6% have been responsible for 3 or 4, and 35.7% have been responsible for 5 or more years. Okay, that was the breakdown in the year 2000. Okay, but now, in the year 2020, right, the sociologist goes out and randomly selects 1,000 caregiving grandparents and obtains the following data, right? So these are the actual observations. They found that of the 1,000 caregiving grandparents that they surveyed, 252 of them had been responsible for less than a year. 255 had been responsible for 1 or 2 years. 162 had been responsible for 3 or 4 years. And 331 had been responsible for 5 or more years, right, for their grandchildren. So we want to test the claim that the distribution is different today than it was in 2000, okay? Well, the null hypothesis is that the distribution is not different today than it was in 2000. The null hypothesis is that it's the same today as it was in 2000. Well, what was the distribution in 2000? The distribution in 2000 was that 22.8% had been responsible for less than a year. So if I call that group 1, right, if I call less than 1 year group 1, 1 or 2 years group 2, 3 or 4 years group 3, and 5 or more years group 4, then the null hypothesis is that P1 is still 22.8%, just like it was in the year 2000. P2 is still 23.9%, just like it was, let me do that, 23.9%, just like it was in the year 2000. P3 is still 17.6%, and P4 is still 35.7%, right? That's the null hypothesis, is that those proportions have not changed. The alternative hypothesis is that at least one of them is different than it was in the year 2000, right? So at least one PI is different than it was in 2000, okay? Or you could write at least one PI is different than claimed in H null, right? Something like that. Okay. I'm not going to check conditions on this. Our sample size here is 1,000. That's pretty large. In fact, because our sample size is 1,000, we can figure out the expected values pretty easy. Right? The expected value for group 1 would have been, right, we multiply this number by, well, actually, we multiply this number by 1,000. That just means moving the decimal 3 times. So the expected value, E1 is 228, E2, 239, E3, 176, and E4, 357. All of the expected values are bigger than 1, and all of them are bigger than 5. So we can go ahead and run the test, right? But anyway, so to run the test now, we go to stat, goodness of fit, chi-square test. I'm going to write down a little abbreviation, chi-square test. All right, this is the Greek letter chi. All right, so it's the chi-square test. Okay, let's do it. So the first thing we need to do is enter the data. And in fact, well, actually, I'm not even sure you need to enter the data. Let's take a look. It's been a while since I've done this, so I'll have to remind myself. But we're going to go to stat, goodness of fit, chi-square test. Yeah, so we need to have a column where we enter what we observed. Let me do. We enter what we observed, and another one where we enter what was expected. So what we observed, that's the data that the sociologist collected, right? So that would be these numbers right here in the chart, right? She observed that of the 1,000 caregiving grandparents, these were the numbers that had been responsible for their grandchildren, right, a certain number of years. Okay, so that's what we observed. What we expected is what we wrote down in the null hypothesis. Okay, so this is what we expected to happen. This is what we observed to happen. So let's write those things down. So what we observed was 252, 255, 162, and 331. Oh, shoot. I hate it when I do that. 252, 255, 162, and 331. Okay, the expected values, that's what we wrote down in the null hypothesis. So it's 0.228, 0.239, 0.176, and 0.357. Okay, so we're going to go to stat, goodness of fit, chi-square test. So observed and expected, and then hit compute. And one thing that you'll notice is that it takes your expected proportions and it turns them into expected counts. In this case, it doesn't make a huge difference because our sample size was exactly 1,000, so it was just a matter of moving the decimal places over. But if our sample size had been, 250 or something, then these numbers here would have been quite different from these ones. But anyway, the most important thing in this output table is, of course, the p-value, 0.0856. Now, if alpha were 0.1, this would be good enough to reject the null hypothesis. But I think in this case, alpha is supposed to be 0.05. So that's not quite small enough, right? We're not going to be rejecting the null hypothesis. So let's write that stuff down. So 0.0856 is the p-value. So since 0.0856 is not less than our level of significance, right? We were supposed to test at the 0.05 level of significance. We do not reject. Okay, in other words, right? If we assume that the proportions haven't changed since the year 2000, then there would still be a little over an 8% chance that we would have collected the sample statistics that we collected. And so at the 0.05 level of significance, that's just not good enough to cast doubt on the null hypothesis. So we're not rejecting it, okay? So at the 0.05 level of significance, there is not sufficient evidence to support the claim that the distribution is different today than it was in the year 2000. Okay? And that's that. Okay, so that's that question. So really not terrible, right? Same kinds of steps as before. It's just now you're testing more than two proportions. Okay. Let's do another one. Back to M&Ms. I guess I like M&Ms. I don't know. Anyway, Mars Inc. claims that there are 30% brown, 30% yellow, 10% blue, 10% red, 10% orange, and 10% green candies in every bag of M&Ms. We randomly select a bag of M&Ms. We counted the number of M&Ms that were of each color and obtained the results shown. At the 0.05 level of significance, can we conclude that the bag that we purchased agrees with the manufacturer's claim? If they do agree, then we would expect 30%, 30%, and then 10%, 10%, 10%, 10%. And I have my doubts. I think we're going to be rejecting the null hypothesis here, but let's see, right? So this time we've got 6 colors that we're testing. 5 and 6. The null hypothesis is that the proportions are exactly what Mars claims they are, right? So P1 equals 30, P2 equals 30, and the rest are 10. Okay, the alternative is that at least one PI is different than claimed by Mars, or, you know, in the null hypothesis or whatever, right? So let's run the test, right? It's stat, goodness of fit, chi-square test. Let's see what we get. I guess before we run the test, we should probably put in the observed and expected counts. Oh, but I've got to make this different than what it was before, so I don't get mixed up. So I'm going to call it obs and exp. All right, but the observed count 17, 17, 27, 13, 9, and 6. The expected counts, or expected proportions, were 30%, 30%, 10%, 10%, 10%, 10%. Okay? Now let's see what we get. So stat, goodness of fit, chi-square test. We want to compare the observed counts to the expected counts, right? Oh, I was wrong. We're not rejecting the null hypothesis. That's an even larger p-value than the previous example. Well, so I was wrong. I guess there's not enough evidence to reject the null. If you look at the expected counts here, you see now a difference in the numbers, right? So in order to get these, they did what we did by hand on page 2, right? They said, well, your sample size here was 72, right? 72. If you add up 17 plus 20 plus 17, you know, you get 72. Was that right? Is it really 72? 70, 37? That's like 40 something, 50 something. Okay, yeah, 72. Okay. Anyway, your sample size is 72. So if you multiply 72 times 0.3, then you get 21.6. If you multiply 72 times 0.1, then you get 7.2, right? And that's why these ones are 21.6 and these ones are 7.2. So these are your expected counts, right? These were your expected proportions. These are your expected counts. So if you compare the expected counts to the observed counts, I mean, here you're off by about 4 candies. Here you're off by, you know, 2 candies. Here you're almost dead on. Here you're off by like 6 candies, and here you're off by 2, and here you're off by 1. But anyway, I guess the expected count, or I guess the observed counts are close enough to the expected counts for us to not reject the null hypothesis. That's surprising to me. But there you go. So our what was our p-value again? That was 0.267. Okay, since 0.267 is not less than 0.05, we do not reject. Okay, at the 0.05 level of significance, there is not sufficient evidence to support the claim that Mars Inc. is wrong about the distribution of M&M colors. Okay, so there's not sufficient evidence to support the claim that Mars is wrong about the distribution of M&M colors. That doesn't mean that Mars is right about the distribution of M&M colors. It just means there's not enough evidence to say that it's wrong. And maybe that's the problem, right? We only had 1 bag of candies, right? 72 candies. Maybe if we collected, 10 bags or something, then even if we ended up with the same sort of proportions, because our sample size is larger, probably our p-value would be smaller. And maybe it would be enough to reject the null hypothesis. But we don't know. We just don't have enough evidence, right? We don't have sufficient evidence to support or to say that Mars is wrong, okay? So Mars could be wrong, but we don't have enough evidence to say that for certain, okay? That's that. You have, what, 6 problems for homework? That's not, that's not a ton of homework on 12.1. That'll do it for that.